But before we then can run the demo, there is going to be some PowerPoint slides, but somebody told me that you can't be any longer than 17 minutes of PowerPoint, then people doze away. So I will try to get to the demo within 17 minutes at the longest. So I want to then talk about standards describing a test process, following those standards and accelerating the test process. That's the point of my presentation. It's going to be about code coverage and change-based testing. The idea that as you test, you execute only those test cases that are affected by a change of code in order to achieve results quickly, in order to more quickly identify the faults than the software. At the end, there's going to be a short live demo. I set up a board, and it's been waiting to go into action, so we will be very brief on the PowerPoints. I don't want to say much about motivation. You know, software is becoming more and more important. You know that software in the vehicle becomes more and more important, takes over more functionalities, increasing complexity, increasing size of software. And I heard a number in 2017, it was around 100 million lines of code in an upper-class vehicle. It's of course getting more with ADHS. It's getting more with the driver assistance systems, so that doesn't make it any simpler. And driver assistance systems, I wanted to be politically correct, and yeah, in Germany we've got a gender debate there. I got driver assistance systems for masculine drivers, male drivers, a lot of time, and only a few female drivers. So, greetings to the interpreters. We love challenges. And it's not really a challenge because in English it's only just driver, male and female. Whereas in German you have to make a difference. So, quality, speed and price are the essential factors, and the challenge is to keep them acceptable. We know that we cannot make any compromise on quality. Either we get expensive or we get slow. With accelerated test methods, we hope to keep the quality high and to accelerate the development and to then get more into this impossible area in the middle. How do we want to do that? With test automation, change-based testing, complete testing, continuous testing. The more we test, the earlier we test, the earlier we will detect the faults, and the more affordable should it be to remedy the faults. Now, in order to furnish evidence for that, some studies are shown here, some numbers, which are evidence of the fact that it's more affordable to find faults earlier and to remedy them earlier. At the bottom left there's an IBM study, Google study, and at the bottom right there is a study where about 250 projects were studied. On the whole, it's quite clear and understandable. The earlier you find the faults in earlier phases of the test, the more affordable will it be to remedy the mistakes. It's extreme at Google, so where there is a factor of 1,000 between early detection and late detection. So the point is to find faults as early as possible, to keep the costs low, in order to keep the quality up, in order to keep the time to market low, short. And you might believe now that we need to find all of the faults in the unit tests and none at all in the system tests, then we're more affordable and faster. Unfortunately, it's not that simple. In the system test, the focus is in a different place. In a system test, you will find different types of faults that you won't be able to identify in the unit test. So the point is to find as many faults as possible in the unit test, and the point is also to do the system test as early as possible. And doing the latter means that the developer and the development process needs to be given a system at hand which enables the carrying out of global test cases that test interconnections. We already talked about agile development methods, rapid prototyping, having a system as early as possible that you can test. And apart from that, most of the time you won't start from scratch, but you will further develop existing software, the software that is being changed, that you can test on a continuous basis. And if the developer makes a code change and can run then tests immediately and not only at the end of the test, then abolishing the mistakes is more affordable. So, test as early as possible, as much as possible. Then code coverage, we also mentioned it several times before today. It's interesting if you are dealing with software development in the widest sense. So please join in now. Who of you is working in software development or in a team where software development is taking place or in a company where you are developing software? I think now gradually I'm about to catch all of you. So hands up once again. Who of you knows that code coverage is being measured in your field in this area? And now code coverage in the system test. Please leave your hands up. Leave your hands up. So not many hands are remaining. Code coverage measurement in the system test certainly is a major challenge, a bigger challenge, but it also delivers important findings on the topic of testing the software. How complete was my testing? How complete are my test cases? And in my demo, I'm going to revolve mainly about this topic of system tests. Code coverage measurement is an important metric. That's why many of you and your companies are already doing that. Auditors, for example, want to know that you tested the software well. You have to prove it by delivering the metrics code coverage, because there's something that the auditor needs to have at hand in order to be able to confirm to you that you did testing well. On the other hand, code coverage helps you to find test cases, not only the unit test, but also the system test, so that you know which areas of the software were tested well or bad. We once did that, or I got numbers from customers who said, we want to go away from a black box test onto a white box test. The old test cases that we used to carry out, we take them and we check about how many code coverages we have accomplished with our previous text. And one customer had 45% code coverage, the other one 55%. So basically half of the software was executed. You may find that good, you may find that bad. It definitely gives important indications to see which parts of my software I've tested and which not in higher test levels, not only the unit test. Where would it make sense to be more accurate in testing? Maybe there are some software areas where it's not that important. For other parts that are more complex or more central and crucial, maybe you should go into more detail in testing. Then code coverage analysis helps us in change-based testing. If we want to decide which test case needed to be carried out again, then the code coverage measurement happens to be an important information in the context to get that done. For the sake of completeness, this is a rough overview of the entire test process and where change-based testing fits in nicely. You certainly know that. You should begin testing as early as possible. Static code analysis is important. Then unit testing, integration testing, system testing. I know in automotive there are even more test levels, but it's supposed to show that we are going from small to big, from isolated part that you test very intensively to the wider whole. How should you test? Of course, functionally. First of all, black box, nothing against it. You need to make sure that the thing does what it should. Functional testing. Only after that, we take a look at code coverage, find out how good or bad our test cases are, add some in order to catch missing branches. We are not finished yet. We can still test the system for robustness, minimum test cases, maximum values, put them on the keyboard, maximum speed on the motorway, whatever. Testing is a permanent process, a continuous process. Interesting colors. This was accepted to be green, but it doesn't matter. Regression testing means we test not only once, but if we further develop a product, we carry out all the tests again. Regression test normally stands at the end of a product development. And here we go. Continuous testing means that we test, for example, every night, executing all test cases, or after any code change, we execute all test cases, which is, of course, a problem due to the runtime. If your system test runs 3 weeks, then you can't make a system test every night. How can we solve the problem? For example, through parallel testing and through change-based testing, so that you don't say we blindly execute all of the test cases, but only those affected by the code change. Parallel testing can be done very well for the unit test. That is something that mostly you don't do on the embedded hardware. You would do that in simulation. You can very well parallelize unit tests because they're independent. So maybe you want to test only a single C file or a single function. Change-based testing is quite clear and obvious. On the left-hand side, you can see the source code. On the right-hand side, a random number of test cases, no matter whether unit integration or system tests. You apply a code change. The question is which test cases need to be executed, those affected by the code change, and by way of the code coverage measurement, we can decide that. We say if this function wasn't used in the first place in executing the test cases, then I don't have to execute this test case again because the code didn't change. We don't expect any other results in running the test again. That's the entire underlying concept, and I'm going to show you that. I stayed below 17 minutes. I spent only 14 minutes on my PowerPoint. What I've got here is a board of Renesas with RH850 with an ARM processor through a CAN cable connected to a VN1610, which goes to the laptop via USB. I stick the board on. Also, then vertically here, below that there is a Renesas E1 emulator which is needed for flashing and for debugging. That's the debug interface. And functionally, it goes together as follows. On the right-hand side, you've got the board, the RH850, which can be seen here via JTAG connected to the emulator by Renesas. Through the Greenhills debugger, the JTAG interface, we are using this debugger for flashing purposes and also so that the coverage data taken back from the target system back to the host. On the other side, we've got Canoe connected via CAN bus with the board for the REST bus simulation. You know that for Canoe test cases, for executing test cases, and also for a special thing, we've got a special CAN bus message that we implemented, a previously unused one. We sent that one to the board to say, well, please communicate to us the coverage. So the coverage on the board, we remember it in bits as to how many lines were executed or not. Those who participated in the workshop yesterday may remember that at some point in time, at best at the end of the test case, we sent that kind of message to the board. The board knows that it's expected to communicate the coverage information, and then we get it via the debugger from the board. We store it on the PC. One might have done it differently, by the way. We've also got implementations where we transmit the coverage through the CAN bus, but it goes through the debugger, and we need the debugger anyway because we want to do flashing. Because if we do change-based testing, then the code that is changing has to be newly instrumented. It has to be newly taken onto the board, and then accordingly the test cases have to be newly executed, and then the debugger interface is just simply faster. This is the test setup. On the top left, we've got the source code. We are using vector cast in order to instrument the source code. So we add additional code lines that put the bits in the memory from which we read the coverage. This is solved through a Python script, which is worth mentioning because it's a very flexible opportunity then for communicating to vector cast how the application can be built. It may be possible that you've got an EDA that you want to script or whatever. What are your test cases? What is the name of the executable? Where are the test cases supposed to be executed? What is the command to execute a test case? You can all implement that in the test script. When the code has been instrumented, it will then built into the instrumentation, will be flashed into the board via the debugger. Then we've got a COM interface to the Canoe. The test cases are built with Vitess Studio, and this COM interface is an interface by Microsoft for software-software communication. It's got nothing to do with the old serial interface. It's a purely software interface. Vectorcast asks Canoe what are the test cases that you've implemented, and then says via the COM interface execute individual test cases. At the end of the test case, a CAN bus message is sent in order to say communicate coverage, get coverage, and through the debugger it will then be written into a file, and Vectorcast then maps it then to the test case. This is what it looks like in theory, and here we should be able to see what it looks like in practice as soon as hopefully I remember my password. As we can see, we can't see anything, but here we go. Okay, Canoe is running here. And the board that we want to test, or the software running on the board, is a self-written one, very fundamental, very basic software, in order to simulate a central locking depending on the speed of the vehicle. So we've got a button in the vehicle where we can say central locking on or off, or doors locked or not, and depending on the vehicle speed, the door is supposed to be either locked or open. I don't know whether you can recognize the lamp shining in green. As I increase the speed, you could see that around the green lamp blue dots are added. Speed increasing, that means, and from a speed of 25 kilometers per hour, central locking should strike. In Canoe, I've got a small panel that I defined where I can change the speed, and the door lock symbol should tell us whether the red lamp went on or not. I don't see it. I just rely on Canoe. If I increase the speed, you are going to see, as I hope, that by now the vehicle is traveling at 272 kilometers per hour, which is unusual in the vicinity of Stuttgart, not easy. Red means door locked, and you should see the blue dots, which means speed is high. If accordingly I reduce the speed now, then we should be seeing that the door comes open again. I don't know what you would expect from a central locking. It should remain closed when I get to a red traffic light. But once again, that's only a simple implementation intended to just solely show the principle. In the background, we've got Canoe running, doing the rest bus simulation at the moment. And that's the test cases here that we've got from VTest Studio. In VTest Studio, we've got this completion processing. The completion processing on each test case sent the dump coverage canvas message, one canvas message telling the board, get coverage, transmit coverage. So if I allow such a test case to run, and I closed the wrong one now. The first test case that we are seeing here in Canoe is one where we are accelerating, put in on the gas pedal. So we should see the blue lamps becoming more, seeing that the vehicle is then becoming faster, then the red lamp goes on, lock is being active from the desired speed level. And this is checked in order to find out whether the software is working. This is not about Canoe, but the point is that we can control everything from vector casting, that I do each test case individually, I measure the test coverage per case. For that purpose, and somewhere in the background, we've got vector cast running. What's behind that, once again, is the implementation in a Python script. Those are the points where we can say what's the make command, where should test cases be executed. So the communication with Canoe has been implemented here as well. And if, for example, I make execute full, so for execute all test cases to be executed, then through the comment interface they go to Canoe asking what test cases do you have, then each test case is executed individually. We should see Canoe then executing the test cases individually. At the end, the coverage will be communicating, it will be stored, the information will be stored in a file, and it will be added to the vector cast cover project. So the lamp should be going on and off. Of course, that's going to be checked whether central locking is working, yes or no. At the end, we should be seeing that we have executed all of the test cases. Why? Because we haven't got coverage. If I do that again, then you can see the advantage of change-based testing, because it's very fast now, nothing has been changed. We didn't have to execute anything because all test cases had already run. I can, of course, take a look at code coverage here in VectorCast. I can see test cases at the bottom, and I can click individual test cases or the coverage results for the test cases to check which parts of the code have been executed. And I can see here from the green lines which lines have been executed. The yellow ones indicate partly executed. For example, this if statement here with the exit true has been executed with output true, but not with output false. So we went through that log, but we haven't got this one branch. Red means lines not yet executed, and thus the code coverage analysis helps to find the test cases, saying that, well, there is a branch that I should be trying out in order to check whether the code at this point is also working as it should be. If I select all results, then you will see that we are rather well off in this one file at least. We've got a lot of code coverage reached, 100%. That's why we've got a tick there. And if you fly over individual lines with the mouse, you then know the test cases then for individual lines. And if you want to check where we should be doing even more testing, then there is an overview for that as well. For example, you can take a look at the functions that were all tested. That's the cyclomatic complexity on it, code coverage that has been achieved. And you can also sort according to cyclomatic complexity, for example, and you would then find that the most complicated functionalities haven't yet been tested, which of course is a little bit alarming, and it should be alarming because the more complicated code should be double-checked, certainly really, in order to make sure that it actually does what it's supposed to do. Now we want to do a change-based test execution. So we take a look at the original code and we build in a mean error, mean fault. So we close the door only at 250 kilometers per hour. GNU should notice that and complain about it. And now, if accordingly, now I restart the build, then now the amended file will be newly instrumented. The Python script calls up the batch file for the make, for building the application, the instrumented application. Then a look is taken at the test cases, first the build and flash. That's why the debugger opens, flashing it onto the board. Board goes into operation. Then there are some funny lights there, nice to see, hopefully. Then what are the test cases that are affected by the code change? They are newly executed. Shouldn't be all of them, but only just a handful. And after that, we see the results in vector cast. Like, for example, here, we see that 3 test cases out of the 12 test cases were executed. Not all of them, but only part of it. So we didn't newly execute the 9 ones because they were not affected by the code change, and accordingly, it was not necessary to run them. What about the results of the test case execution? You can see that here in reporting. We can see which system test cases worked and which didn't. And from here, you can jump into GNU again. So a colleague from London, he wrote a plugin for that purpose, where you can see which test cases were failed. And through a double click on failed test cases, the report in GNU will be opened. That was already it. I tried to gain some time. I didn't want to surprise you. Well, with regard to test design, we could take a look at some detailed information on that, but we are already 5 minutes behind our schedule, so I don't think this is necessary. Thank you, Ingo Nickles.